So today marks the end of the third event, Accelerating Progress. And as Mike said, we are very grateful for all of the work that's been done by all of these committees and by the Challenge Series funders, AFRL, SUNY, IBM, AFOSR, NICE-Tech, and Ensign, I'm sorry. So without further ado, I'd like to bring on and introduce the speakers that we have today, who are all awardees who put in proposals and were selected for funding. So Lindsay, we have our first speaker. All right. Hello. How are you?
Hello. Good.
Our first awardee is Dr. Theodore Chasby. She is an assistant professor in computer science and engineering at the Department of in the Computer Science and Engineering Department at Texas A&M University. She has numerous awards, including a very recent, as I understand, NSF Career Award. And her research interests lie in the areas of effective computing, signal processing, data science, and machine learning. And the award that she will be receiving is entitled Investigating Human Trust in AI, a case study of human-AI collaboration on a speech-based data analytics task. So welcome, and the floor is all yours.
Thank you so much for the kind introduction. It's really great to be here today and listen to all these very interesting presentations and discussions. So today I will be presenting our research as part of the Trustworthy AI challenge on enabling trustworthy human-AI collaboration with emphasis on a speech-based data analytics task. So the increasing use of AI in the military gives rise to questions about how much AI can be trusted by their users. There is evidence that suggests that dimensions of trust in automation and trust in AI are common. However, despite the similarities, those two actually might not always have the same dynamics. So the goal of our work is to investigate dimensions of trust in human-AI collaborative data analytics task, identify human-based factors and system-related factors of trust that might actually affect this joint collaborative interaction, and build an evidence-based model of human trust in AI that also quantifies its effects of the performance in the data analytics task. We will exemplify our discussion via a speech-based data analytics task in which human users are called to collaborate with an AI system in detecting deceptive versus truthful speech. And we specifically chose this task because it's of high relevance to AFRL and the military in specific. So deception classification from speech still remains a challenging task, despite the presence of tangible speech micro-behaviors which were indicative of lying. For example, changes in speech prosody or pause duration can be indicative of deception. Also, when humans are asked to annotate deceptive speech, all annotators are found to fully agree on only 50% of the data approximately. So this suggests that the successful completion of detecting deception from speech would highly benefit from an effective human-AI partnership in which humans and AI can complement each other. So as part of our work in the Trusted AI Challenge, we will recruit 180 annotators who will collaborate with an explainable AI algorithm in detecting deceptive speech. The AI algorithm will be built on acoustic features, essentially features that are related to speech intonation and prosody, in order to identify deception from the data. Annotators will be asked to listen to the speech signals, observe the decision of the AI explanation, of the AI algorithm, as well as its explanation, and then will be asked to provide their decision on whether a speech signal is deceptive or non-deceptive. We will randomly assign annotators into 4 conditions in order to control for the performance of the AI system, as well as the provision of explanation, because these are characteristics that we plan to use in our analysis. Based on the collected data, we will examine dimensions of trust to the AI, including calibration, resolution, and specificity. Particularly, we will examine instances of mistrust and overtrust to AI. We also plan to investigate how precisely the level of trust in AI differentiates the AI capabilities, what is commonly referred as trust resolution, and also identify specific components of the AI that affect human trust. For example, such components could be the performance of the AI system or the level of explainability that the AI system provides in order to justify its decision. We are further interested in the time-based evolution of trust in AI, and we will also examine dimensions of initial trust to the AI, trust maintenance, as well as trust repair. In this example scatter plots of human trust versus AI capacity, we can see a few examples of trust calibration and miscalibration. So we can see that trust calibration mostly will be indicated where we have a pretty good amount of trust that is associated equivalently with automation capacity, while the opposite will hold for trust miscalibration. Similarly, we will want to examine examples of low trust resolution versus high trust resolution. Following that, we will also investigate individual and system-based factors that affect trust in AI. So one of our hypotheses is that users with high expertise in data analytics tasks are likely to depict higher trust calibration and increased trust resolution compared to users that might be more novice to the same task. We further anticipate that annotators who depict high levels of trust propensity and automation expectancy will have high initial levels of trust to the AI, just because people who initially have a higher trust propensity are initially more likely to depict higher trust in the AI system. We also expect that increased trust to a high-performing AI system will be actually there, and we also expect, based on also grounded on findings from previous work, that a system that will provide higher levels of explanation will be trusted more by its users. So we will measure human trust via self-reports, behavioral measures that capture the agreement between the human and the AI, as well as neural measures that were previously found to be indicative biomarkers of human trust. As part of our preliminary work, we have examined trust in explainable speech-based AI. We found that experts' trust levels vary, with some individuals either over-trusting or mistrusting the algorithm. So in the bar chart on the left side of your screen, you can see that this is a ratio that depicts the annotator agreement with the AI versus the annotator agreement with the ground truth. We see that when this ratio is high, this indicates overtrust to the AI because the annotator tends to agree more with the AI rather than the ground truth. And vice versa, when this ratio is less than 1, this indicates potentially mistrust to the AI. So we can see that experts' trust levels actually have varied throughout our experiments. In addition to that, trust changed in our experiments over time, with some experts starting with reduced levels of trust, which increased over time, and some others gradually losing their trust in the AI. So this is, in summary, what our plans as part of the Trusted AI Challenge are. I would be happy to discuss any of the above and answer your questions, and thank you very much for the opportunity today.
Great. Thank you very much, and congratulations. This looks like a very interesting topic. I'm looking forward to seeing your results from it. Thank you.
Thank you very much.
Okay. Our second awardee is Dr. Jason De Cruz. He's somewhere in our background here. He's an associate professor of philosophy at the University of Albany in SUNY. Jason works primarily in ethics and moral psychology, focusing on topics of trust, trustworthiness, self-deception, and rationalization. He has published work that appears in Philosophical Studies, Ethics, and the Journal of American Philosophical Association. And his award is for a proposal entitled Trustworthy AI from a User Perspective. So, Jason, it's all yours.
Great. Well, thank you for the hosts for bringing together such an august group of speakers and such an engaging group as well. I'm just making sure that, there we go, that my screen sharing is working here and that the slides are full screen. Okay, so our project develops the foundations of a trustworthiness assessment framework for AI-driven systems. And we propose to develop the conceptual foundations of a system of metrics that foregrounds context, user experience, and human priorities. And in this aim, we are proposing two novel characteristics of highly trustworthy AI systems that we dub reciprocal trustworthiness detection and rich trustworthiness. Since I just have a few moments today, I'm going to focus on rich trustworthiness. So I should say that our aims are primarily conceptual, and they're aligned with our expertise in moral psychology, in theoretical and practical rationality, decision theory, trust theory, and social epistemology. But our ambition is that in collaborating with AI and ML designers and engineers, including specialists in human and computer interaction, our work will have a downstream effect on the conceptualization, the design, and the implementation of AI systems. Okay, so on the slide over here, on the top right, you see an image of Digidog. And Digidog is a semi-autonomous robot deployed by the NYPD very unwisely in a public housing project in the Bronx, where distrust of the police is already very high. And needless to say, Digidog was not well received. It was seen as a dystopian example of over-aggressive policing. And the NYPD turned Digidog to its maker, Boston Robotics. And so one question we might ask is, what changes to Digidog could elicit a trusting response from citizens as opposed to the distrusting response that it did receive? And a sort of surface fix would be to do to Digidog what you see on the bottom right hand of your screen over there. That is to make Digidog appear more lovable, like this huggable Newfoundland. Give Digidog some fur. And that would be a sort of surface fix to the trust problem. But the deep fix would be to ask much harder questions like, how might citizens come to know Digidog's capabilities and limitations? How might they come to know its assumptions, its motivations, and how might its behaviors become legible to them? How would Digidog or its human partners be held accountable for their actions? And these are the hard questions of trustworthiness. And the deep problem is really not in maximizing trust. Maximizing trust really should not be our aim. The deep problem is in matching trusting attitudes with trustworthy systems in the appropriate domain. And that's what we're going to call well-calibrated trust. Okay, so the idea is that resilient trust, trust that endures, requires matched trustworthiness. And the experience of trust that is not met with trustworthiness creates a generalized distrust. And we have got some good empirical evidence of this. So when a person loses their ability or their confidence to reliably discern trustworthiness, they lose their self-trust. And when a human user loses self-trust, then the trust relationship between the human and the AI system is broken. So the question is, how do we address this problem? And how do we implement a solution in AI applications? So one idea that we have that I'll speak briefly about is this idea of rich trustworthiness that we borrow from the philosophical literature, and in particular, my colleague and collaborator at the University of Melbourne, Karen Jones. So first thing to notice is that no finite agent, whether a human or an AI, can be competent in every domain. Therefore, trustworthiness is necessarily indexed to domains, to tasks, and to parties. Now, as agents with finite information and finite time to search for more information, we need collaborators who are willing and able to identify themselves so that we know where to place our trust and for which tasks. That is, we need agents that are not only trustworthy, but also richly trustworthy. A richly trustworthy AI system must be able to continuously monitor and assess its own dynamic functioning. It must be able to generate signals that are legible to both human agents and other AI systems about what it can be trusted to do. Rich trustworthiness is a step beyond comprehensibility in that the AI system is tasked with producing accurate signals about exactly which dependencies it can and cannot respond to. The trustworthiness of AI systems does not guarantee that humans will trust in such systems. A trustworthy AI may not be trusted because its trustworthiness is not legible or credible to a human user. Conversely, AI systems may win the trust of humans even if they're not in fact trustworthy, but only appear to be so. Human trust in AI systems may be misplaced. Rich trustworthiness in an AI system encourages trust that finds matched trustworthiness because it invites trust only where there is confidence to respond to human dependencies. And as a result, rich trustworthiness is more robust and ultimately, we think, more resilient. Got any questions or would like to be in contact with us, here are our email addresses, and I'll throw it back to Dr. Doorman.
Great, thank you very much. Yeah, another great topic. I think you know, when we have human relationships, we take that time to develop trust, and it's really important to look into how we can do that and not have to stare technology directly in the face. So thank you very much.
Thanks.
Okay, our third awardee is Dr. Kosa Goucher-Lambert, who is an assistant professor of mechanical engineering at the University of California, Berkeley, and an affiliate member of the Jacobs Institute of Design Innovation and the Berkeley Institute of Design. Dr. Goucher-Lambert is an expert in the field of engineering design theory, methods, and automation, and conducts research merging computational analyses of human behavior in design with cognitive and neuroscience models of the designer behavior. And his award was based on a proposal entitled Developing an Extendable Bidirectional Model for Human AI Trust for Joint Action. So welcome. Thank you very much for joining us, and I'm going to turn it over to you.
Okay, wonderful. Thank you so much for having me, and what an incredible event. It's been really special to hear from such a wide range of researchers on great topics. So this work is done in collaboration with John Kagan at Carnegie Mellon University. So we're considering AI-assisted decision-making where humans are the ultimate decision makers. And so, we love these scenarios in which to base our investigations on, and we see countless examples, and we've heard so many during the event in which human operators are making poor decisions to accept or reject AI suggestions from this teammate based on this miscalibration of trust, either over or under trusting the AI collaborator. And so here we examine human trust in AI, as well as human trust in themselves over the course of collaborative scenarios, and how these factors might impact the human's adoption of AI advice. So I want to just share a little bit about some of our prior work in which our team developed a quantitative model to investigate human trust in AI teammates. And so some of the core elements of this model that we're capturing are features such as self-confidence. So this is the human's confidence in their own abilities, prior experience, this is mostly experience in collaborating with an AI teammate, and then bias. So these are biases that the human might have regarding elements about some of the AI's capabilities, as well as accumulated confidence. So how these factors are changing over time. So we applied this model that I showed a snippet of to a simple decision-making task involving chess puzzles. So basically, we developed a collaborative AI to work with the human to suggest different chess moves for this example. And so the basic task procedure was as follows. First, a human would make an unassisted move. They would then receive a suggested and assisted move from the AI, pictured here as Taylor's suggestion. They would then receive feedback on what the ultimate decision was that they made, whether they selected their previous move, took the AI suggested move, or maybe a new move altogether. Then they reported confidence on the AI's performance as well as their own self-confidence. So we tested this across two different decision-making kind of contexts, one in which first the AI had a high performance level and then switched to a low performance level, and in another condition, the opposite took place, where we had a low performing AI and then switched to the high performing AI. And so our results from this prior work showed some key insights regarding how human trust in AI teammates evolves over time. And so some of the high level takeaways that I want to communicate are that, one, there was loss aversion, so that the confidence in AI is gained quite slowly, but then rapidly lost when poor decisions were made. We saw that when the AI is performing poorly, people lose their self-confidence along with confidence in the AI. We see actually, and this is more than we had anticipated initially, that self-confidence really dictates the human decision whether to accept or reject AI suggestions, and that there is what we call a vicious cycle. So that when accepting bad AI suggestions, humans who are termed poor or fair decision makers are more likely to continue to accept the next suggestion, even if it is wrong. And so moving into the one-year AI challenge series, what we propose to do is to extend this framework that we developed in a few key ways. So the first is that we're going to be extending that model, which previously focused on human trust in AI, to be bidirectional. So now we'll also be capturing AI trust or confidence in their human collaborators. We're going to be expanding the team size. So instead of just a single human and a single AI, we'll now be considering teams of 3. For this one-year project, we'll have 2 AIs and 1 human. And then finally, we're updating the application area. So rather than the chess puzzle paradigm that I showed previously, we're now going to be choosing and working with a task based on the configuration design of a drone. So this model extension that we're engaging with for the AI Challenge series has 3 members, and we're going to be measuring the resultant trust dynamics between every 2 agent pair within the system. I want to share a little bit more about the problem application that we're using. So this will use the high-form drone design platform that we previously developed under the DARPA A-Teens project. So here we have essentially humans and AIs will be collaborating to develop a drone. So that's pictured on the left-hand side. There's a variety of components that can be manipulated, such as the battery, different motor pairs, and so forth. And then there's a capability for humans to independently develop a complete drone design on their own, as well as get suggested drone designs from the AI agent that are in response either to incremental steps that the human are making or complete drone design. And these can maximize certain problem characteristics, such as the range, cost, or payload that the drone needs to maintain. And so even with a team size of 3 in this new work, we anticipate very interesting trust dynamics starting to emerge. So we're really interested in which there's going to be scenarios where both AIs potentially may be in conflict with the human operator. And the best ways to integrate the 3 models of trust and the different dynamics, I think, is going to be an area of research not only in this one-year project, but a really rich area of investigation for follow-on studies. So on the left here, I've listed a variety of different outcomes that might happen after each trial, in which, for example, the human selects their own design and then receives negative feedback, or choosing one of the AI's design and receiving positive or negative feedback. Okay, so with that, I'd like to stop there. I'd like to thank again the AI Challenge series organizers for putting on such an interesting and thought-provoking event, and grateful to our prior support from AFOSR and DARPA. So thanks again, and happy to engage with any follow-up if people want to contact me directly. Thank you.
Great. Thank you very much. I look forward to your work as well. A year is a very short period of time, but yeah, I think you have some really good ideas that you'll be able to pursue in that time.
Great. Thanks so much.
All right. Okay, moving on. Our fourth awardee is Dr. Amir Rahmadi. He is an assistant professor in the Department of Computer Science at Stony Brook University, where he leads the Ethos Security and Privacy Lab. His research focuses on security of emerging technologies, including machine learning and the Internet of Things. He works on designing, building, and evaluating systems that tackle security challenges. And we've heard a lot in the past about the security of reinforcement learning, and his project is going to be entitled Verifying Sensor Noise Robustness of Reinforcement Learning. So welcome.
Thank you for having me. All right. So this has been a wonderful event, and I'm delighted to be here with you. Today, I want to talk about our research agenda for this AI challenge on how we can measure reinforced learning model robustness against sensor noise, and how we can move towards systems that are verifiably secure against such phenomena. This is a joint work with my co-PI, Professor Stanley Buck, who is also on the line. So if you have any questions or comments, feel free to reach out to us. So I want to start my talk by talking about the vulnerability of deep neural networks. And in the last few days, I'm sure you have heard time and time again about these vulnerabilities and how these neural networks can fall prey to imperceptible noise that can cause them to misbehave and produce wrong results with high confidence. In this slide, for example, you see yet another example of this phenomena, where a model that classifies an image with very high confidence as a pig misclassified it as an airliner when targeted noise is added to the input. And this has been shown again and again throughout different types of neural networks. But one question we need to ask from ourselves is that, should we really care about these attacks? One may argue that if the adversary has enough control over the system to modify the input to the machine learning model in such a fine granularity, that they most likely have already acquired complete control over the system. And thus these attacks are not really realistic or needed in the physical world. And we are dealing with these neural networks in physical worlds, and they are taking actions and today. We have seen examples of them in consumer products, like Tesla self-driving, and in the aviation front, like the airborne collision avoidance systems. However, we believe that the answer to this question is still yet a resounding yes, and that we should, in fact, care about these attacks. And the reason for that is recent works have showed that these attacks are not really limited to the digital domain. One of the more famous examples of these attacks is our 2018 work, where we show that you can fool visual classifiers using stickers that you put on road signs and make them misclassify a stop sign, for example, for a speed limit sign. And there has been many other works that showed similar attacks. For example, glasses, 3D printed glasses that can fool face classifiers, and 3D printed objects that can be misclassified. And even beyond these adversarial attacks, we know that environmental noise and sensor failure can have a catastrophic effect on how these systems work. And a recent example of that has been the 737 MAX series, where a sensor failure causes the MCAS system to catastrophically fail and cause multiple crashes. So the question we want to address in this challenge is, how can we verify the correct behavior of neural networks? And an approach that has recently gained traction is the use of formal verification. And in fact, my co-PI has done some groundbreaking work on this front, developing tools that verify the correct behavior of deep neural network. However, these tools do not consider the scenarios I just talked about, where either targeted or untargeted noise can cause these networks to fail. So the better question that we want to ask is, how can we verify the correct behavior of these neural networks in noisy conditions? And to address this, we propose a 3-step verification procedure that consists of falsification, clustering, and perturbation analysis. In the first step, we want to understand how close are the existing system trajectories to violating a safety or security specification. And in doing so, we want to locate trajectories with minimal robustness that could potentially be vulnerable to such attacks. Next, we want to perform clustering, where we group these trajectories based on the type of violation that may be needed to cause them to misbehave. And we imagine that we can use this clustering in tandem with the falsification techniques to find new classes of attacks. And finally, we want to perform perturbation analysis to find the smallest observation noise that can cause violation in this low robustness trajectories. And to do this, we will take advantage of the toolboxes that my co-PI has developed, along with some of the existing literature on neural network attacks. And in fact, here we show a very early result of our work, where the red nodes show the noise trajectory, the attack trajectories that we have with added noise to the system. We're really excited about this line of research, and we hope to share our results with the AFRL community in the upcoming years. So if you have any questions, we would love to hear from you. Thank you very much.
Great, thank you very much. Yeah, we're looking forward to your work as well. Okay, so now we're going to move on to our 5th awardee, who is Professor Eugene Santos, Jr. He is currently a professor of engineering at the Thayer School of Engineering and an adjunct professor of computer science at Dartmouth College. Dr. Santos' work on artificial intelligence intersects the area of information, cognition, human factors, and mathematics. His current focus is on computational intent, dynamic human behavior, and decision-making, with an emphasis on learning nonlinear and emergent behaviors and explainable AI. Definitely a topic that's very popular these days. And his proposal and the award that he's receiving his funding for is entitled Quantifiable Expectability and Measure Intentions for Calibrated Trust in Human AI Joint Activity. So welcome, Professor, and I'll turn it over to you.
Great, thank you, David. Also, thank you for the organizers and group for this event. It's been very interesting. I've heard a lot of very nifty ideas and, of course, challenge questions. So what I'm trying to do in my proposal, let me just give a brief overview, is looking at the joint human AI activity. We've heard the previous speakers also talk about this, but look at it from a point of view is that trust is a two-way street. Trust is something where you want to make sure that the teammates, whether it's AI or humans, can, at a minimum, for example, expect and understand the behaviors and decisions that are made by each. So what I'm going to talk about here is sort of from the point of view of intentions and the modeling of intentions. And you can imagine it this way. If you want to have calibrated trust, And you know that trust changes over time. You know, we've already had some other speakers already talk about this, that, you know, over time, you know, it could drop off or it can increase. But calibrated trust really needs to know that both sides have the right model of intentions, or the right just view of intentions of, you know, of the other entity. So that gap in that is our first step in looking at, hey, you know, are we really getting at trust? Because we're trying to, of course, avoid the extreme where, you know, the human decides to turn off the AI, or the other side, of course, the AI decides to completely ignore the human. So just also a little bit of context set up. I'm going to talk a little bit. You could think of it from a point of view that if we're doing an intelligence analysis task, whether say it's information seeking, then you can imagine that there's human AI helping each other in that one. But we'll also go more broadly than that. So where am I coming from? You know, when I talk about intentions is really about, you know, what's the context, what's the goals, what's the beliefs, you know, that, you know, a particular entity, you know, has in mind when they take in actions. So, you know, what's the basis for those actions? And there's a lot of things. I'm not going to go into detail on intent, but, you know, you have things like, you know, what are they currently working on? You know, it also includes, you know, what their past training is, and a lot of different elements. Now, we're not going to necessarily try and cover all of these, but it's to keep that in mind that as we build out a system that, remember, one thing I said is that it's for both, you know, in a team, it's for both partners to have a good understanding of each other. All right. So here's this, is that if I wanted to talk about why intent, of course, is important, it is about modeling the other. So, you know, we typically often assume, like when I was just even talking about user modeling, is that the AI is just modeling the user, the human analyst. But at the same time, if we want to really talk about collaborative trust, the human also has their expectations of the AI. So all these things come into play, and then it gets even broader. You know, whether it's just, you know, the machine and the human in a joint activity, it could also involve the organization, you know, what they're functioning in, and other organizations. So there's, you know, lots of different scales of this involved. Now, having said that, let's thin it down a little bit, where we talk about, in decision making and behaviors, which is what I'm going to focus on as part of trying to build that model so we can measure that trust between the human and the AI. These are all capturing things such as the what, the how, the who, and then of course the why. Now, among this, in the why, of course, is to be able to talk about, what's the reasoning, and then what's the explanation behind what we're seeing, why a particular partner takes a particular activity. Now, what I'm going to jump into is some of the prior work that we have that's going to form the foundations for this effort in trying to figure out how can I compute calibrated trust. I forgot to also say one thing. Calibrated trust, of course, is very dynamic. We're going to see trust go up and down in the long term, but also in individual contexts. So that's a challenge. In a particular single task, how the trust goes up and down is something that we would like to also be able to capture. So let me start off with this. Some of you may know reinforcement learning. Actually, probably most of you know reinforcement learning, but some of you may only know what inverse reinforcement learning might be. Let me put it very simply. Inverse reinforcement learning, and actually you might consider it a misnomer, is about really, I don't know what the rewards are. I don't know why somebody would take an action at this particular time. So it's trying to figure out what the rewards and reward structures are. This way, it's like, it might be because, they have a particular preference that they have to do things in a certain way. They have a particular goal that has not been explicitly stated. These all come in and impact this reward. So in inverse reinforcement learning, the reward is missing. And what we've done already is that we can show that, when we observe the decisions, the sequence of decisions made by a particular agent, let's call it agent, whether it's either the human user or the AI, or even a team, we can infer that and then already demonstrate that those rewards allow us to identify actually who the agent is. So something that simple already that we've been able to verify. Now, the second thing is that with that, let's talk about interference. Interference is what you expect. It's a simple concept, right? If I have two people work together, they may interfere with each other positively and negatively. Negative is the one that we usually think about the word interference, but positive is that, hey, serendipity might happen when you bring together, two minds, so to speak. And if we can capture this interference, Then this gives us the second pillar of being able to understand how the team is evolving. You know, how are they really working together? So this picture here is a fairly simple picture. You know, I could show that over time, which is the bottom x-axis, and then a measure of inefficiency. Obviously, higher up is more inefficiency. And you can change inefficiency to performance. So you're going to have a graph where one way to look at it is that if I had each of the agents working alone, they'll have their own performance or if inefficiency or efficiency trend and graph, and then you can see what's happening with the team. And a simple definition is negative interference is when, wow, it's going way up, and positive interference is when the team's running much lower, okay? Now, with interference, let me just jump into this. So even though I said about that, you know, we look at, you know, information seeking, information retrieval, we also applied this to StarCraft 2. For those of you who don't know what StarCraft 2, it's a multiplayer real-time strategic combat game, all right? So in this one, just for those of you more interested, what we set up was that first of all, there's the default computer player. Okay, it's an AI, but we're not going to really talk about it. That's just the setup. But what we do is that we do have teams going in. And in these teams, they could be teams of bots, they can be humans of bots, and teams of humans. And the idea is that we can do the inverse reinforcement learning, trying to figure out the reward structure of the individual agents, as well as the reward structures of the teams. And all I'm going to talk about in this graph is that, hey, these graphs are showing that, one, it can classify well, and two, it actually does a decent prediction of what the team performance is. Now, why is this important? Now it leads us to the following. You know, we have recent work, and actually this is fresh off, you know, hot off the presses, recent work where we've been doing a lot of studies on human-machine teams inside StarCraft 2. And what we want to provide is, you know, what does interference tells us? What do the rewards tell us? And what we can say, and I'm just going to say it briefly, is that there is adaptive behavior as the human plays with a particular bot. Some will prefer certain bots over other bots because maybe they can understand them better, or maybe they don't understand them. And then at the same time, they also show a level of personalization. And by personalization, this is when we looked at the reward values themselves, is that, yeah, they tend to react this way in this situation with respect to this bot. So, you know, what we're trying to do then is that when we take all these interference and these reward values, then we're developing the metrics and have the opportunity to really jump off and look at some real world problems. In this case, some of the targeted test beds that we're going to be pursuing for the year include, as I said, information retrieval. That is, you know, how can the AI help the human analyst in, you know, in analyzing the text, bringing in the right information, analyze the images, and trying to figure out, again, the difference is that did the AI properly expect or understand the intentions of the humans, and did the humans understand the intentions of the AI? And then other things that we have is we've already developed is that we've been working not just with StarCraft 2, we've developed in, you know, OpenAI Gym to develop a drone swarm simulator that addresses our problem. And then, of course, we're also open to other applications. So we're looking forward to, you know, talking to the folks in this community and always looking for ideas of test beds and, you know, a lot of collaborations and discussions. Thank you.
Great. Thank you very much, Eugene. Yeah, the quantifiable aspects are essentially important in this domain. So look forward to seeing what you're producing. All right. So moving on. Sorry, it's such a rapid fire here, but I look forward to all of these speakers being given more time later on to present their results. Our next speaker is Dr. Taylor Johnson, and is an associate professor of computer science at Vanderbilt University, where he's affiliated with the Institute for Software Integrated System and directs the verification and validation for Intelligent and Trustworthy Autonomy Laboratory. And I won't, very vital, I guess. That's a nice one. You must have taken a long time to come up with that, but it's very, very appropriate. Dr. Johnson is a recipient of an AFOSR Young Investigator Award, among many others. And his title of his presentation today is Verification of Autonomous Systems, Hyperproperties in Machine Learning. So Dr. Johnson, I'll turn it over to you.
Great, thank you very much. So I'll tell you a little bit about our proposed work that we'll be exploring within the Trusted AI at Scale Challenge series. And and thanks to all of the organizers. I've listened in over the past few days and really appreciate everything that's been explored. So I'll start with a little bit of background. You heard a little bit about verification from one of the speakers, I think Amir, a couple talks back. But what we're building on, and I'll introduce a little bit to you what formal verification is, in case people are not too familiar with this. This, in the automated formal verification case, is basically to take a system model and a specification and have an automated method, typically called a model checking algorithm, that returns that the system satisfies the specification and give proof as to why. And if it does not, determine why the system violates the specification and produce a bug or a counterexample. So we've been exploring this in the context of verifying neural networks, as well as the usage of neural networks within closed loop systems for some time. This is our tool called NNV that performs this type of task for neural networks, as well as closed loop control systems where a neural network may be in the feedback loop with some plant model. So a variety of references here. And what this can allow you to do is this picture from the CVPR paper from Amir a couple talks back. This would allow you to show the absence of these types of behaviors. So things like adversarial perturbations. So this is all available online. There are a lot of references here that if you're interested, you can check out. So let me tell you a little bit about what this means in the context of neural networks. This is typically done for systems like digital logic circuits or software for programs. But increasingly, we're interested to explore this within machine learning systems. So I'll primarily focus on neural networks. So you can think of a neural network as a function, at least if it's a feed-forward or convolutional neural network, you can think of it as a function that maps inputs to outputs. If you have this is set up in a regression type framework, but if you have classification, all that can be handled as well. So what you're aiming to do here is, if you have a set of inputs, propagate that set through the neural network and determine what the set of outputs are under that set of inputs. So this is basically computing the image or the range of a function representing the neural network under a set of inputs. So that's the goal. Then computationally, how this is done in many of the approaches is we represent these sets as some form of polytopes or polyhedra and propagate them through and determine some set of outputs. So a lot of what's done in this space so far is considering a specification in the output space and that this is just some set. So there's some limitations of this. And what we're exploring within this project in particular is how would we write down that specification. So we are proposing to use hyperproperties to do that, which I'll tell you a little bit more about. So what does this look like? Just to give you a little bit of a picture so you can imagine a bit what this would look like. If you consider this very simple feed-forward neural network, it's quite small. There's an input set that's basically a cube, and we have some specification in the output space. And we'd like to compute what is that set of outputs and then check if that intersects with this set that represents our specification. So you can compute this. That set is represented as the union of all of these different polytopes in the plane. And then you could sort of visually see that there's not an intersection between these two sets. This is set-based, so you're considering all of the points here in this input space. So what's shown on the right is just an evaluation for 8,000 points. So basically showing that all of the evaluations that you take for this neural network are in fact contained in the set that's being computed. So we'll also explore this in the context of autonomous systems. And for these, typically we're looking at things like safety. For these, we'd consider traces, and in the context of an autonomous system, a trace is typically a trajectory or solution of a differential equation or generalizations thereof. And this would amount to computing the set of reachable states for this type of model. And the system would be safe if the intersection of an overapproximation of the set of reachable states and a set representing unsafe states is empty. So a very similar type of problem, and this is kind of some of the origins of where this came from. So a little bit, I know we're, I think, running a couple minutes behind, but a little bit about our approach for this particular project. Let me tell you about what hyperproperties are. So the reachability approach we just discussed is sufficient for verifying robustness of neural networks, so proving the absence of things like adversarial perturbations, as well as evaluating closed-loop autonomous systems when learning-enabled components like neural networks are used in tasks like perception, planning, or control. But the real major open challenge within this space is what should one of these learning-enabled components, like a neural network, what should it do or not do? And we're going to explore hyperproperties as a language for describing these. So I'm going to be informal, but of course, behind the scenes, we need a formal syntax and semantics for all these things. So basically what a hyperproperty is, we first need to describe traces. I showed you a picture of a trace, but it's basically a sequence of states. And this could be variable valuations or in a program. A property then, in the classical sense, is a set of traces. And we typically use languages like linear temporal logic for discrete systems or signal temporal logic for continuous systems. So then a hyperproperty is a set of properties. And the intuition is that to violate a hyperproperty, you need a set of counterexample traces. So where that shows up in neural networks is if you consider doing something like classification, local robustness to an adversarial perturbation, which is pictorially shown, is in fact a hyperproperty. And this is pictorially shown where you typically be trying to show that a classifier is robust, which would be the bottom case, or if an adversarial perturbation exists, that's essentially the top case. So we're going to explore this for some perception problems, as well as in planning and control problems. So the overarching claim that we're evaluating is that we think this will be a reasonable specification framework, as this shows up even in other contexts like accuracy evaluation, stability of a training algorithm, and so forth. So we're going to explore this in a variety of case studies, some of which are currently being developed with AFRL. Particularly, there are a couple of my PhD students who are ND-Seg fellows with Karen Hobbs at AFRL this summer, developing a safe reinforcement learning framework with Act 3. So that's going to be one use case where we're going to explore this. We'll also explore benchmarks that have come out of the community, such as those through VNNComp, the verification of neural network competition, and ArchComp, which are both relevant competitions in this domain. So that's a little snippet. I hope that was useful for everyone, but I'd like to thank everyone. And to summarize, we're exploring hyperproperties. I also want to thank my group. Zheng Tran really has led a lot of the work that we're building upon that we've been exploring through an ongoing DARPA Shared Autonomy project. So of course, we're grateful to DARPA, as well as earlier engagements with AFRL and AFOSR. At the fireside chat, there were mentions of programs like VFRP, SFFP. So I participated in those in the past, and I strongly encourage those for other faculty to consider exploring. So thank you.
Well, thank you very much. Yeah, I thought this work looked familiar, and then yeah, the assured autonomy was just being developed when I there, and I was reading some of the work that goes on there. So thank you very much. We appreciate your contributions there.
Thank you.
Okay, moving on. We got two left. Our seventh presenter today is Yiming Ying, who is a professor at the Department of Mathematics and Statistics at SUNY Albany, and currently leading the machine learning group at Albany. His research interests here center on the research topics of machine learning theory, deep learning for imbalanced data, which is a big problem, optimization, and trustworthy machine learning. And he has an acronym FRAP, Fair, Robust, and Privacy-Preserving Machine Learning for his talk today. So welcome, Yiming. Turn it over to you.
Thank you, David. It's my great pleasure to be at this wonderful conference from which I learn a lot. So thanks to the organizer to organize this wonderful conference. So today I'm going to talk about a little bit about my project, which is developed based on collaboration with IBM. So special thanks to Kush from IBM, also other members from the machine group at Albany. So let me actually give a little bit of motivation about this project. And the whole story of machine learning is trying to minimize actually loss function and maximize the prediction power. And we heard a lot of actually stories, amazing stories about the performance of deep learning which actually surpass actually the human performance. So, but in reality, when we deploy machine learning algorithm or AI system in physical world, especially in high-stake applications such as health care or autonomous driving, and we want to make sure actually machine learning to be trustworthy. So to see, we already heard a lot of wonderful talks about what's the trustworthy AI. So in this project in particular, I think I will focus on the following element of trust: robustness, fairness, and privacy, and also their interaction with generalization. So there's a lot of definitions about how do you measure actually the fairness, how do you define actually privacy protection, how do you define the robustness for machine learning models. But there's actually a key missing piece in the theoretical aspect is how actually different elements of trust interact with each other, and also how they interact with generalization and accuracy. So in this actually project, we proposed to use a very central concept, which is stability as a common ground to study the interaction between different elements of trust. Stability is a very easy understand actually concept. Basically means stable conclusion or decisions to appropriate perturbation to the data. And also, I think stability is not only appears in machine learning theory and statistics, and also appear in many other actually scientific fields. For example, in dynamic system, in partial differential equation, and also physics to describe our natural world. So it makes it natural to concept to as a high level actually concept to start as interactions. So let me actually describe a little bit actually our prior work and also why explain actually stability. It could be a very good common ground to study the interaction between different elements of trust. The first of all actually is in terms of the relationship between stability and robustness. In the classical book by actually famous non-parametric statistics, statistician Hempel in his book. Robustness basically means a kind of stability theory. Right? Of course, the robustness can have different meanings, as we heard from the previous actually talk. So for example, the first one is distributional robustness. So in this distributional robustness is kind of stability performance of the model, which when actually the distribution shift appears from the test data and the training data. And also adversarial robustness basically means the stable predictions to the adversarial perturbation of the input data. So in this kind of both kind of robustness actually problems, it can be formulated a minimum maximum optimization problem. So basically is a defender and the adversary is playing a chess. The adversary is trying to actually mimic the worst scenario to destroy the stability, while the defender is trying to minimize the worst case loss, which the aim is to increase the stability of your learning system. And also there's actually deeper actually relationship between stability and generalization. In particular, stability can imply generalization. So what's generalization? Generalization error is just the differences between the test error and the training error. And we want to actually this generalization error as small as possible when we design actually machine learning algorithms. Stability plays a key role to study the generalization error. So in particular, we can use the uniform stability concept to bound the generalization error. So uniform stability basically means actually the follows: if you slightly perturbate the training data, and if the output does not change too much, basically means is uniform stability. So stability implies generalization error. And there's a lot of studies, in recent couple of years to study actually the stability of stochastic gradient descent in various settings, and also in minimum maximum optimization problems, which we obtained in this year in ICML. And also, in terms of actually stability plays a role to study actually privacy preserving algorithms. And a good actually notation for privacy preserving is called differential privacy. So if we look at the definition of differential privacy, is very closely related to stability again. Okay, so what's a differential privacy? Differential privacy basically means if you slightly perturbate data, and if you see the distribution of the output of your learning algorithm does not change, and then we say this is differential privacy, and we have parameters to quantify actually, the privacy budget, which is epsilon delta. And again, actually, in these kind of studies, interaction between the differential privacy generalization and robustness, actually, we have a recent paper study actually, using stability techniques to study, how can we guarantee the machine learning algorithm is differential privacy, but at the same time, actually attains the statistical optimal generalization performance. So hopefully I actually convinced you stability is appeared in different actually element of trust. And it's actually a very good common ground to study actually the interaction between different elements of trust. And the picture basically is actually, our target in this project by furthering address, many questions about, for example, how actually the interaction between the fairness, which is we are going to focus on, in this project, and how can we actually use the stability concept to design new trustworthy machine learning algorithms. So that's my presentation, and thank you for having me here. I'm looking forward to talk to you about this topic in this community. Thank you.
Great, great. I'm sure there's a lot of people that also look forward to hearing from you. All right. So our final awardee actually also wins another award for the furthest streaming video. So he is a professor, Dr. Peter Bruza. He is a professor of information systems at Queensland University of Technology in Australia. I guess according to my calculations, you must be having your first or second cup of coffee right now, up pretty early. His research spans cognitive science, non-classical logic, and information retrieval. His current research lies in the field of quantum cognition, which aims to develop new understandings of human cognition using conceptual frameworks and a formalism of quantum theory. And his proposal was entitled An Interactive Model for the Calibration of Dynamically Changing Expectations of Human and AI Systems to Promote Trusted Interactions. So, Peter, it's all yours.
Okay, thanks for that. Thanks for that introduction, and thanks everyone for allowing us to present at this conference. The presentation that I'm going to give is going to be, I think, different to the ones that I've managed to see thus far, and then that we're attempting to really look at things from the human side. And as the introduction suggested, a part of this is really trying to use some of the theory and conceptual frameworks of quantum cognition to try and come up with a better understanding about how to model trust, and in particular expectations of trust and how they might differ between the perceived trust when someone is interacting with the system. So I'll start with just some positioning. So you can imagine a system here. Someone is interacting with an AI system, and then essentially what orthodox cognitive science assumes is that when the person is interacting with the system, they'll be in a definite state, a definite cognitive state with regard to whether they trust or distrust the system. So another example of that is if you're modeling someone that's in a jury, and they're listening to the evidence against the defendant. The assumption is that the cognitive agent will be in a definite state of whether they're guilty or innocent, and they might change, or there might be certain dynamics, but at any given time they'll be in a definite cognitive state. Now, one of the key differences with between classical cognitive science and quantum cognition is it draws on some of the aspects of quantum theory that actually allow us to look at cognitive phenomena in a completely different way. So what I've got here is a photon, and a photon is an indeterminate phenomena. And so what can happen is that they can measure a photon at a particular axis, and then you'll get the spin up and down of the photon. Or you can take another different axis of measurement, and you'll get another reading of spin up or spin down. The important point here is that before you get that reading, the photon is in a completely indeterminate state. So it's not that we don't know what it is, it's just that the fundamental state of being of the photon is indeterminate. So quantum cognition, if we translate that, is we can think about different trust dimensions like reliability and benevolence, that these are dimensions that we're looking at and measuring, and with respect to a particular indeterminate cognitive phenomena that is trust. So what's happening here is from a quantum cognitive perspective, we're seeing trust as an indeterminate cognitive state like a photon. And what we're trying to attempt is that we can, by using some of the machinery of quantum physics, we can attempt to model holistic sensing of trust across different trust dimensions. And in our project, we'll be looking at reliability and benevolence. So let's go back to this example. So the way that we're modeling the human agent here is that their trust is an indeterminate state. We're going to use quantum cognition that's going to come up with a holistic sort of model of trust expectation. But of course, the interesting question is, well, what is the match with perceived expectations? So what we're going to do for this is we're going to use a model, a bistable probabilistic model. And as the name suggests, bistable probabilities sort of draw the analogy with bistable percepts. So if you get the Necker cube, this is a phenomenon that you can only see one perspective at the time. You might flip-flop between the different perspectives. Bistable probabilities try to model the situation where the human agent is even different between different decision perspectives or different dimensions of trust. So so what we have here is we have this H here is a human agent. So we're going to be model that with the quantum holistic trust expectation model, and then they're interacting with the AI system. And so that the expectations are being holistically formed, they're interacting with the system, and then perceptions are being formed of the actual trust. And the interesting thing is how much of these align. And this parameter K here is a way we can model the degree of alignment between the holistic trust expectation and the perceived expectation. So this is a purely dynamical model that'll update over time. So then when we come to the experiment, I don't have time to go through it. We're going to have three different, we're going to have a scenario, and there'll be three different conditions. And these blocks here represent as the subject is going through interactions with the AI system. And so we're going to use a mock AI system that we can sort of change in the background. And at different points, we're going to do an expectation audit. And so we're going to audit their expectations of trust. Then we're going to intervene in the system and sort of like affect its reliability or its benevolence or a combination between the two. And then we're going to do a trust audit. And so to give an example of how we can do that, so when we do an expectation audit, when the user or the human agent gives their response to that, they'll be somewhere in this grid. And we're also going to give we're going to read off what their confidence level is in regard to their expectation. And when we get that sort of collect data, we can use that to prime these things. From quantum physics, they're called POVMs. So these are the things that allow us to model the expectations holistically across the dimensions of reliability and benevolence. So, and at the same time, we're going to look at neurophysical things, and then we're going to we're going to collect EEG, and we're going to try and determine the neural correlates of the expectation confidence in trust and the degree of trust in the simulated AI system. And so one of my colleagues here at Queensland University of Technology, he works in the EEG area, and we can develop sort of different algorithms to sort of read off and try to learn classifiers where we can get the level of confidence or a sense of trust from the EEG data. So just to summarize the presentation, what we're trying to do in this project is we're trying to model a gap between a human agent's expectation of an AI system and their perceived trust while interacting with the system. And we're taking sort of like a human-centered approach where the modeling is coming from a novel angle, and that's from the field of quantum cognition. And the outcome will be an empirically tested theoretical quantum-based model for the calibration of dynamically changing expectations of the human, in order that we may come up with trusted interactions with an AI system. So that's my presentation. Thanks for your attention.
Great, thank you very much. We appreciate your work and look forward to seeing your results.
Yeah. Thank you for that.
Okay, well, that's about it for the challenge series. Again, I'd like to thank all of and congratulate all of the speakers today, all of the awardees that are going to be working on this problem over the next year, and all of the people that have gone into making this event happen, both in front of the camera and behind the scenes, and especially to my now good colleagues, Amira, Bryant, and Mike, who we've met with almost every week for the last year and a half. I think this has been very successful, and I want to thank you very much for working so hard on this, and we look forward to continuing the progress.